Hello everyone, welcome to my shop. I'm Robin. Today we're going to be taking a look at the Nikon Comparator rebuild I've done, and this isn't a complete rebuild of every single detail of everything, but it covers some of the interesting aspects of what I had to do to rebuild this. Got this very cheap, and it turned into a really nice comparator, extremely useful, and as most things, I wonder how I got away without one for so long. So let's get to it. Here's the comparator in its final resting place. This is the right hand door, which I never opened to go into the shop, and so I can just pop my head out the door from the shop there. You'll see I've got one of these folding, a wide folding stool to stand on, because this thing was made for giants. My eyes are a little bit low on the screen for viewing this without that stool. So everything came out really nice. The table all reground, you see in place, and the micrometer head, the V-block reground. Generally really pleased with this thing. This has a huge 15-degree helix angle adjust, which most comparators, some comparators don't even have a helix angle adjust, and some of them that do have a very limited range. And the back dovetail there you can see in place, and we've seen all the redo of the ways, new fasteners, new paint on the panels, little body work on the panels to get them all the dents and things knocked out. Drawer unit's working nicely. And then we'll come down here and take a look at the lens drawer, and this has nice pockets for the lenses where I can just reach in and grab like this, but the ends are protected. The plastic's actually snug on the ends. 10, 20, 50, and 100. The 50's in right now, but this keeps them totally protected. They're solid, but yet you can just grab, and you're not unwrapping them, taking them out of a box and all that carrying on. So always thinking of ways to make things efficient that you don't hesitate to do them because they take too long. This used to be the end of the comparator where the door was, and those kind of cabinets are, in my mind, just a total waste of space. So you stick a few things in the front, you forget what's in the back. And that's why we integrated the two drawer units that I found at a home goods store, and you'll see some footage there where I put those in. The micrometer head just needed some cosmetic work. Redid the zebra stripes on the display, and it's real happy. It's a 2-inch travel and zeroable, inch metric, reads 1 micron in metric, 1/10 an inch. Saw a 4-inch travel digital indicator in a sales flyer, and I realized that would be perfect for this vertical travel because it's just about like 4.1 inches for stop to stop on this thing. So that really worked out nicely, and now gives me digital readout on both axes.
These are pictures of the comparator that I saw from the industrial supplier that had it, and in general it looked like it was in fair condition, but I could see the rust was on some of the areas. That indicator never showed up, so I got a credit for that. There's the cabinet, had several overlays in there, which was nice. You see the lenses on top. In general, the whole outside was not in too bad a shape. Main problems were the rusty table and the rusty vertical travel system. There you can see it's really bad. Was very rusty. So here you'll see coming up how bad the rust was on the rollers. Those are the 2mm rollers, and then there's a picture of the whole thing with the rusty rail.
Now we're looking at the main reason why everyone but me stayed away from this comparator like the plague, and that's because the main travel way system of the main tabletop was completely trashed by rust. This actually looks immensely better than it did. This was all bright orange rust, and this rust is fairly deep, but I don't care, because this is a roller system where it uses 4mm by 25mm rollers in here, and they were completely rusted. This was pretty rusty, but cleaned up pretty well. The cage. This holds the rollers in alignment and keeps them perpendicular to the axis of travel so that they don't track off. And then these are the little cages for the two sides of this. I believe it's maybe 60 degrees. I haven't actually measured yet. But these go on either side holding 2mm by 7mm rollers. So this forms a roller table system, so it's very low friction. There's two constant force springs that sit on here that pull the table against the micrometer to maintain position. So this is simply a matter of regrinding these surfaces till they clean up on both pieces, reestablishing the height of them such that they actually bear evenly, because they have to be just right that you get, as these sit properly, this is parallel. So you've got 2mm gap here, 4mm gap here, and until you get those heights exactly right, these rollers are going to hit one end or the other until you get it parallel, where they're hitting dead parallel across there, and you get full even bearing. So that's about the only tricky part about doing this regrind is maintaining that. I can dress that. This is the focus axis of the comparator. This is the swivel base that sits on the knee and allows helix angle adjust. It pivots on that and slides on this surface. And then they're using basically a ball V-way type arrangement where they've got 4 5/16 or 8mm ball bearings, a hardened rail, and then in the actual iron base here, they've got spring steel inserts. And as you can see here, we look at the actual surface where the balls ride. You can see that, well, number one, this has had rust, but also that line contact isn't the best. For the focus axis, it doesn't really matter that much, but you want it to be consistent. So I just happen to have some 6mm crossed roller packs. Now these are about 7/8 of an inch shorter than what I need, but I can cut it in half, put a 7/8 spacer between these. And this line contact, cylinder on plane as opposed to ball on plane, will have much better load capacity, and everybody will be much happier.
Here's the dovetail where the rust was on the dovetail section, and here's after I stoned with precision ground flat stones and WD-40.
So I'm walking through the home goods store with my wife, and I see these cabinets. They had casters on the bottoms, and all the handles were on there. I already had the wife strip them down. 2 of them there, sitting there. One's got a dent in the top. And I look at it, and I say, what? $29? I haven't even got the comparator yet. I bought it, but it had not arrived yet. And I said, you know what? I think those will darn near fit 2 of those in sideways in that comparator base. And then I'd have tons of actual usable space, drawers for lenses, whatever, inserts, any kind of relatively light. These don't have fancy drawer slides. They're literally just sheet metal slides, but they work reasonably well. So that's what I'm working on. I'm going to actually insert these 2 in there.
Using the roll-in saw to split this square plate into 2 corner pieces for the casters.
Look at that nice clean cut, because it was cut long ways. A lot easier on the blade teeth also. I've got all my corner plates stacked. I have a caster on there located with some clearance for the silicon bronze rod fillets that will be holding this to the sheet metal. I've got my upper right corner set as 0, and I'm going to drill and tap through all of that right in that location, and then I'll just crank off the actual bolt or the slot spacing of the caster. There we go, all 4 holes tapped. Now we just have to make sure we put them on the right direction, flip them the right way so that we have the casters oriented in the correct location on the base. Here's the frames from the 2 drawer units tacked together, tacked into the hole I cut in the wall of the old cabinet. It's all bronze, TIGS brazed. And now I'm going to drop the bottom in that I've already pre-done
with the 1/4 inch thick reinforced corners already drilled and tapped, flattened, and that's ready to go. So that's nice and flat, and it's going to sit down and sit on the bottom of the units, so that actually will support the bottom of those. That's going to sit flush on there, and then that'll get spot welded and TIG brazed into the base. Here's the bottom before I get ready to prime it, put the casters on. TIG brazed the support pieces in, and severe Bondo job on making this look like $1 million compared to the original welding. So yeah, I'm going to put the casters on it, flip it over, and put some paint on it. Here's the base. I have all the sides filled in with body putty, but the top is a really wobbly mess. So I'm just put a painting tape dam around the outside. I've got it leveled, and I'm pouring in some potting, a compound that I had left over from a job, and that's just going to level out this top. It's probably got undulations maybe as high as 1/8 of an inch. So I'm just going to pour this in and let it rip. So this stuff's very fluid and will be self-leveling, and should have a mirror finish top when this is done, but it's going to get painted over.
This epoxy flows very slowly, so this is sped up a lot, but you can see how it just wets out and just flows, and you'll see my reflection there. There's the cabinet with all the body work done and a fresh coat of paint. Here I have my Renzetti 30, 60, 90 blocks aligned and indicated in on the grinder, getting ready to do the dovetail grind.
Here's the traverse across there. Basically just a jiggle of the needle on a 50 millionths indicator. And I've accomplished that by putting a shim in the bottom here and adjusting its position so that I can tweak the setting there. I thought this was a 60-degree dovetail because I have these angle blocks that we're sitting on are exactly 30-60, but it's not, so I have to shim to get that angle correct.
That bar and toolmaker clamp that you see there in the middle is where I'm pulling a slight bow out of that dovetail so that it's actually straight on the flat mounting surface. If I didn't do that, there would end up being not uniform across pin measurement on the dovetail when it gets bolted to the main frame. So you'll see me tweaking things here, just watching how it's grinding and gently adjusting this till I get the response that I'm looking for grinding wheel wise. Yeah, this, you can mess things up easily doing this, so be careful if you're replicating this. I'm used to tapping these things around. I know how tight I have it, so I can get away with just nudging this and seeing what the grinding wheel's doing. Then once I've got this where I'm happy, and I traverse and do a full traverse grind across there to grind that face so it cleans up. And there it is, finished ground. Here I have the part clamped to a 246 block so that I can measure over pins to see how parallel the grind was from end to end.
Using the surface plate with the silicon carbide paper glued on to clean up and deburr this back surface where we're going to be sitting to grind, and make sure it's not twisted in this knot. It's nice and flat. Changed my mind on the setup since this was actually 60 degrees. It's a lot quicker to just put my 30, 60, 90 blocks on, indicate in on this, and move. So you can see how I've got room to clear the grinding wheel here, to clear the wall and get in and do the 60. And I'll be able to flip it 180 and do the top, which gives a better finish, this edge, the second operation. You can see we have clearance. But in each case, this back surface has been indicated in, so it's dead nuts. So that's 0, 0 on that 60-degree surface on both of my angle plates back here. So that's already been trammed in. And I'm fortunate to be able to just grab relief. I'm actually using the
V-way for that was for the focused travel, and that's what we're clamping with so that we don't distort and we have a good grip without being in the grind zone. So grinding on this face at 60 degrees, I have to adjust in this axis to get that face of the original dovetail to line up. The back's aligned, but you got to get that lined. Taking 1/1000th off this face, actually off both faces, 1/1000th off each face, will require 2/1000ths removed from that surface. It's just the trigonometric relationship of those two surfaces. So I'm going to remove 1/1000th off the bottom there, and then there's the finished ground surface, and we'll move over to the other side. Now I've just flipped the part, and we are indicating it in again, and we've indicated on the back surface back here to make sure that that's aligned in that direction. And now we're going to remove 1/1000th off of this surface, and you can see we're clearing the wheel there, and we had to adjust the twist in this angle to get that to line up properly, and then we go ahead and remove 1/1000th from that face. And there's the final grind of the female V. Now we've moved on to the table, and we're doing the male V on the table, and we've indicated that in, and we're grinding 1/1000th off that face.
This indication, edgewise, when you're doing something on angle plates like this is very important. You need to make sure that the angle plates are indicated in, but in this direction, you have to pick a reference that you're going to use to align, especially when you're flipping apart. So I'll use that exact same edge when I flip it to make sure I've got the exact same alignment, because that definitely influences where you're grinding here. It will change the actual alignment of that groove. So even though the setup looks like it's quick and dirty, but you have to really indicate things in very well in all directions. Okay, here is indicated on the actual tabletop, which is important. So you can see we've got 0, 0 reading there. So with the edge up here and this face both running true, we know we have the axis of this running true to the tabletop. So when we grind this actual way surface here, it is going to be parallel in two directions. If you're ever wondering why I think these modified vice grips are so cool, this is a prime example right here. I don't know what else you can get in there with to be able to get in there clear and yet still have room to get off over the part, over the edge like that. These things just really come in handy. So now we're going to take a look at the indicating. I'll try to do this without running into the indicator as I indicate. So I'm sitting right there, and now I'm going to traverse my marks here. This is my other mark. Same places that I marked before on the opposite, when I had it the opposite direction. You can see what I'm doing here. I'm making sure I've got the exact same tram so that the axis, when I grind this face of this way, is going to be parallel to everything else. There's the last V surface, ground, in this same setup.
We're going to grind the flat now where the purple Sharpie is, and you'll see how we align that. We're grinding the flat way, and we've removed 2/1000ths from it, and that gives us the relationship of the 2/1000ths on the flat to the 1/1000th on each side of the 60-degree V.
Just in case you think Mr. Bozo never shows up in my shop, this is where the coolant nozzle got caught and the wheel sucked it through, pushed the wheel off center on the hub, and then took a swipe on here. Fortunately, because this is a roller set up here, it's not going to cause any issues functionally, and it's out of sight. So not the end of the world, not happy about it, but yeah, not a likely death situation here.
So now we have the saddle mounted on the grinder table, and the comparator table that's been finished ground sitting on top, and I'm grinding the flat of the saddle to the right height so that as we traverse, we will get parallelism once we get it ground to the right height. And since the 2-to-1 relationship of the 60-degree V and the 2-to-1 relationship of the rollers that were being used allows these to sit metal to metal, and as you can see, we get a nice parallel traverse there when it's ground to the exact right height.
So I changed my mind, and I'm going to make the actual bearing strip thicker to make up for the difference from the 8mm ball to the 6.5mm cross rollers. So I'm looking around the shop for something. I want to do it now. I want to get it done today. And I'm looking around for some heat-treated material that I already have. So I have these caliper bodies. I know you guys are going to cry, but I have lots of these laying around from stealing the heads off them before we started buying the heads separately as a repair item for digital readouts that I make for special grinding equipment. So I'm going to whack these off here and grind them down to 0.75 thick, which will split them in half, and then I'll grind them down to my 3/16 wide, and those will be my bearing strips. More sacrilege here. Here's what the grid pattern looks like on the calipers underneath the coating. Pretty neat stuff. These are peeled off the back. So now I've got my two places where I'm going to be able to get my 0.75 by 3/16 wide strips, 150 millimeters long, out of some reasonably hard material. So I ran a cutoff disc down through the depth rod groove in the calipers to split them in half first. So I'm going to take them down to the 3/16 wide first, then I'll take them down to the 0.75 thick. That's what your chips look like when you blast an awful lot of material. They get like steel wool, and you're taking heavy cuts with long working teeth. There they are, ground down to 3/16 thick. These are all the long hairy fibers of steel, that steel wool I was talking about. Now we'll do the thickness. There they are, ground down to 0.75 thick. I've dusted both sides. Make sure that they're parallel.
Here I'm grinding a little notch in the rails that is clearance for where there's an M3 screw that holds these rails tight into the V groove in the cast iron. So I have to put that on all these.
Here's one of the cross, well in this case going to be cross roller rail. And I've just dusted this face, and I just used my V-block. I have the outside surfaces of the rail stoned nicely. Take this out, clean everything, put this back in, grind the other side, did the same with the others. So these are exactly centered and the exact same depth to the back, which really doesn't matter. But that's how we cleaned those rails up. It only took a few thousandths to get rid of the rust and get a really nice grind finish on there for those new roller packs to ride on.
Some of these large headed screws that are used to hold the panels on the comparator were damaged. They were actually smashed shut, and some of them have drive swell from it, the bit not being engaged properly. And in my mind, when you're sort of restoring something and want the appearance to look kind of new, there's nothing like a nice new fasteners to brighten things up. And I'm not a fan of Phillips screws if I can avoid them. So I got these flanged head button heads to get the diameter to be big enough to be a corollary to the ones I'm replacing. And it's only like $6 for 25 of these, and I think I only needed a little bit more. Bought 2 packages of them, so trivial. But at the bottom of the comparator, they have these, which were special screws. These are Bakelite, phenolic resin, whatever you want to call it. And obviously these didn't survive as well. Some of them got stuck in the threads, and this is M16 by 2 thread. So how do I replace these? And yeah, of course I've got a lathe and a CNC and all that, and your first thoughts are, oh, I could machine these and do the metric thread and turn the heads, but I'm trying to get this thing rebuilt and not make a project out of it. So then comes to mind, hey, why don't you get the same style screw as these? That would look really nice since they're on the same face. And put that on there. Well, that works, and obviously this diameter here needs to be at least as big as this one because it has a pretty big hole in it. I think these large screw holes were done for tooling purposes of machining the casting. So that's the only good reason I can think of that they would do something like that. There's 2 of them on each side of the panel or of the frame. So I get this as the largest that I can get from McMaster, and it has appropriate head size, but it's not the right thread size. So just a lot of people would know this trick, but I buy a piece of all thread or a bolt or whatever you can get that has the right threads on it. This is just a piece of stud, 16 by 2 stud. And I'm just going to drill and tap at the M10 thread here, part off a piece such that this becomes an M16 screw like that, but with this head on it. So not rocket science, but not something some people might think about. You can take your pick between Loctiting this into the frame and having this screw go in and out, or Loctiting the threaded portion on this and letting it stay with the screw. Really doesn't matter. Just that one or the other works, because if you don't do one or the other, you'll end up where this will end up driving through the threaded portion will end up driving through the frame and not engaging. So you need to tie it down one way or the other. So you ever have those duh moments where you go like, oh, that was real bright. After I get done machining these, I say to myself, oh, I bet you McMaster car has a threaded insert for this. And then hopefully to justify me making them, I was thinking, yeah, but they're not going to have the right thread combination of M10 by 1.5 inside and 16 by 2 on the outside. Guess what? That's standard. I could have got 5 of them for $13.62 from McMaster car. So if I thought a little further through that, I would have bought them instead. So just a note to keep in your mental arsenal. The protractor ring on the comparator is out of round. I think this thing sat out in the rain for a long time and it warped this. I believe this is a casting and has been machined. So I'm using the knee of the Bridgeport as a press to gently press this, and I've got an indicator zeroed here, and the difference in diameter reading is a good 20-30 thousandths. So I'm going to gently press on this a little bit using the dial on the knee as an indication of how far up I go, and until I get a reading of where it responds and actually takes a set, and then I'll start comparing the heights, as are in different locations around here to make sure I'm getting it as round as possible.
So what you see here is a broken comparator screen where I propped up the comparator and left it, and it fell over and cracked the screen. So I bought a disc from the local glass place. They cut a nice round disc, and I'm going to show you how I engrave the lines in it and frost it.
So I'm using the calipers here to measure the diameter of the glass, and this isn't super critical, but it's what I'm doing is to use this to cut the halfway between this, whatever this diameter is. I'm going to go in the middle of that measurement for the distance from here to the edge of the glass. So that's why I'm measuring that. Now that I have that measurement cut in two, I've actually moved the bar until I've got that dimension. The 2 thousandths, 2.5 thousandths, or whatever that in theory I should account for the thickness of that blade, but there's more than enough room for that, and not to mention the fact that thing's probably not even anywhere near that round. It's just cut by the glass company, but they did a super nice job. Here I'm grinding the beveled edge off the razor blade length. The razor blade's 8.5 thousandths thick, and I'm going to grind it down to 4. That's going to be our lap width. As you can see here, we've removed all the bevel. This is 8.5 thousandths thick, and now I'm going to grind this down to about 4 thousandths, 3.5, 4 for, I don't know, 10, 15 thousandths. That's going to be our lap section. You can see I've just touched off here on the 8.5 thousandths thick section. I'm going to diagon that and put the get my width that I want. I don't want it too wide because at 4 thousandths thick it's going to be pretty flimsy. So here's our groove lap to cut the groove in the glass. This is 4.5 thousandths thick where I ground it down here. And you can see I put these radius scallops in here, and that's to give room for the diamond slurry to get in between and actually feed and lap in each of these positions. If I just left it straight, basically the center section would get starved. You'd just have what could climb in at the ends. Even on the ends I have a bevel there so that the diamond is encouraged to get down under and roll down through there. Just have a piece of bamboo that I lap flat on a piece of sandpaper on the plate to glue to this to be a backer to hold this firmly and straight against the reference rail. Right here I've just super glued some washers on to have the lap stop at about 3/8 of an inch from the edge. Carrying that groove all the way out to the edge is just inviting that plate to snap in half. Remember, we're creating a stress riser in this, and we have to be very careful. There's no guarantee that I won't get halfway through this and have the thing crack through the groove that I put in here. So just pray for the best. Okay, we're going for it here. Hold this in place, snug. Put a little stuff on the outside. Take an actual travel here and try to get a little slurry lined up on the edge there. Now I'm going to use both hands to gently press down and in.
I'm using the multi-anvil mic to mic over the actual lap to determine how deep the groove is. So I put the measurement, take the measurement while the lap is down in the groove, and then I move the lap up off the out of the groove, put a little spacer behind it so it sits on the glass surface, compare those two measurements to determine how deep the groove is. Don't need much, just need enough for the epoxy to have a place to embed in the groove.
Okay, one of the things that I pondered about how to get these crosshairs, even though they don't need to be exactly centered, they do need to be exactly perpendicular within reason. So thought about a lot of different ways of doing it. Wanted to keep it simple. So what I'm doing is I've had this on. You've seen me do the first groove. The first groove's in there. It's roughly 3.5 thousandths deep. Now I need to place this bar exactly 90 degrees, exactly the center line of the diameter. So what I'm doing is I'm putting this block on. I have tape pads under here to contact on the glass. I have a clamp ready, and a lot of this was strategic planning on exactly where I'm going to be able to put clamps as I move. So I have this long clamp, realized that okay, I'm going to go from here to here with this bar. I still needed to be able to clamp two places here. So I did all that planning beforehand to make sure that when I got to moving to the next position that I would actually be able to do it. So I'm going to set this up now with the calipers to have this be the midline dimension. Clamp this down, release the bar here, clean it off, slide it up tight against this in this direction, clamp it down, remove the block, and mount the second groove.
Gonna let you in on a little secret. This is actually the speed I work at all the time, and all the rest of the videos is actually slowed down. So I just wanted to let you in on that.
Okay, I think we're done. Take the clamps off. Hope nothing pops here in the process of getting the clamps off. Get this off without cracking the glass. I think we're home free. Oh yeah. So let's see what's going on here. Let's just take a peek at this. There's the lines right there. Put a scale in here just for reference. Rule, actually. A rule in here for reference. So you can see those lines are finer than a rule division. Yeah, just a little bit finer than a rule division. So now I need to fill those in with black. So I'm going to use some JB plastic weld. Very good high strength epoxy. This is like 3,500 psi, so very strong epoxy, and relatively quick setting. Blend this up first before I put carbon black in it to blacken it up.
We're going to add carbon black to the epoxy to darken it up. You have to make sure you add sufficient amount of carbon black. The lines in this are only about 4 5 thousandths wide and about 3 thousandths deep. If you don't have enough carbon black in there, it can look dark until you spread it thin, and then it will just be kind of grayish. So you need to have a really good load of carbon black in there.
Stuff on there. So now I'm going to go over and put this on the glass. Get an angle here that works without blowing out the camera. Over here on a different angle. While this epoxy is curing and in the gooey state, I come along here with a razor blade and just scrape off the excess, leaving a strip there that we can just wet sand down until we get to the glass. And then we will frost the entire glass with diamond. These are the lines after sanding off the epoxy. The lines are 6 thousandths thick, read with a little pocket microscope. So this is where experience comes in feel of what's going on, knowing what tumbling abrasion feels like as compared to, a charged lap. Even though this lap has what looks like a charge, that's just where it's been rolling. So I think this is good where we are here. I might put some more diamond on for this other part, and then we're just going to start going around the whole thing. I switched to water for my vehicle. Vehicle is the trade term for the carrier of your slurry. So I'm using water here. The alcohol evaporates too quick, and all we're after is something to somewhat lubricate, help the abrasion process go to town. So I've switched to water here for that purpose, and I'm just keeping it wet so that we don't have any sludge buildup. We don't want to cut with sludge. We want to cut with free rolling diamond particles. One thing that's difficult is with it being wet, it's hard to assess its level of frosting because when it's wet, the frost kind of disappears. One thing I didn't mention is this is a silicone cooking mat, and the beauty of the silicone is, number one, it gets a death grip on this glass so it can't move. It also keeps relative motion from happening with any slurry or grit that gets underneath, and if this is shifting around, this would end up frosting the back of the plate, and we don't want that to happen. We only want frosting on the front face here where the engraving is. There's a section I just cleaned off with alcohol, and we've got a pretty nice uniform frost there. Now, one thing I want you to see all the black? That is the aluminum being abraded, and that is actually ideal because we know that the aluminum's not charging. The aluminum is being abraded by the tumbling action with the glass, so that's perfect. If I charged the aluminum lap completely, washed it off, and started cutting this glass, you'd see no aluminum residue because the aluminum would have a grip on the particles and there wouldn't be anything to actually cut the aluminum other than the glass fragments. The glass swarf would act somewhat as an abrasive. So that dark that you see there is actually a good sign that this aluminum and glass is a good combination. This is one of those things where experience and thinking about graphically thinking about the mechanics of what's going on with these particles is important. When I did glass on glass, you would think, well, they're equal, so everything should tumble. But there's the aspect of it that the glass has almost zero ductility, and therefore the particles don't want to embed and get a bite to initiate a roll. Whereas the aluminum being ductile, as these various particle peaks are sticking up, they actually poke into the aluminum, get enough traction that aluminum is rolling that particle. So that's, I'm not saying that's exactly what's going on, but that's the way my mind is processing what's going on to make decisions on which way to go. The iron was okay, which is a little bit more ductile, but the aluminum really performed nicely. And initially I thought the glass would be perfect because they'd be equally matched. But then I realized after I felt its action and saw that it was just not getting a good bite, that made me rethink it and say, okay, what's going on? Probably just not ductile enough, well, not ductile at all, therefore not getting a grip on the particle to initiate a roll. Cleaned this off completely just to see what's going on. I can see that there are some stray scratches that are not the perfect uniform frosting here. So the outer edges need to get hit hard, but I think we're going to need to clean off at the very end and do a very gentle pass on here to get a nice uniform frost. The frost looks good. It's really nice. But one of the things I wanted to mention was very important, even though this is silicone, even though this isn't moving technically, it's got a good grip. As slurry and abrasive particles get underneath here, if I left this go for too long, I could get to where some relative motion could cause scratches on the back. So just as a precaution, took everything off, wiped off the back of the glass, wiped off the silicone, put it down clean again, and we'll start over. I found a good section here to show you the difference between frosted enough and not. If I come over here, you see that all reflection is gone. I come over here on the edge and you can see I'm getting a reflection off the original surface of the glass that's just barely been scratched up. You can see the little bit of hazy scratches there. And then as we move into the fully frosted, that reflection just totally disappears. And the light, as you can tell, the light, normally that light would follow as it would go across here. So it's not like some magic where the light's going out. It's gone. So I need to hit the outer edge a little more.
So there it is, completely frosted with the epoxy lines in, and it's ready to go into the comparator. There you're seeing my camera through the frosting on the glass. And there it is, all complete, ready to go. You can see an image up there on the screen of the projection, and going to be a very useful piece of equipment in the shop.